Just so this doesn't go too long, let's look at this for today. And then okay. Oh man, I'm hungry. All right, I'll have to stop midway through this to eat some food, but we could get some of this out of the way. I guess first off, since I haven't looked at this in a minute, let's go through this stuff, huh? Oh, can you even? Yeah. All right. Response time is the time it takes to No, it's from the user's perspective how long it takes to hear back. Are some numbers used to define the system's load? So you'll want like requests per second, read-write ratio. There was one more, I feel like, I can't remember it though. Hit rate on cache. I was thinking that, but I was like, no, it can't be that. A fault is when the system stops performing. No. Fuck. Is when a specific component deviates from its spec. I swear I knew that before I saw it. What are key characteristics of the relational model? SQL, joins, decades of tooling, tables, schemas, yeah. Normalization, strong consistency, structured schemes, tables, SQL, and decades of tooling, okay. What are the downsides of imperative queries embedded in an application? You mix business logic with access logic. So it can be hard to optimize. More error prone. A declarative language is when you... This is when you tell the computer what you want, but not how to get it. Pattern of data you want, the conditions that must be met. The system decides how to get it. What is the benefit of declarative query languages like SQL? You get to abstract how, which means you can optimize it behind the scenes and everyone benefits. Simplifies logic. When your data looks like a document. When you need data locality, flexible schemas, and you can handle duplication. Duplication can be tolerated. Yeah. A mem table. These aren't good cards. This one specifically is an in-memory data structure. Something like a B tree. Yeah, that's it. Not B tree, red black tree. SS tree. B trees are balanced trees. They're always O of log n. Or is it n log n? I think it's n log n. I can't remember the notation, but it's made up of pages, fixed size pages that whose keys point to either data or another page. They represent ranges of data. Yeah. O of log n, not n log n. Always balanced. Fixed size pages, and they have root and page. Yeah, okay. Almost done. Extract, transform, and load. It's how we get data into the warehouse. LSM trees, log structured merge tree. That's it. A concatenated index is when we take multiple keys and put them together to make one single key. Ordering is defined by the index definition. Specification. A covered index is when some of the columns are located with the key. Not all of them, though. An SS table, sorted string table. It's a sorted string table. Shoot. A log file that is sorted by key and is backed by some sort of data structure. Short for sorted string table. Sorting the data makes compaction and merging. Okay, we'll say this is hard. A heap file is a file that contains data to avoid duplication, and we refer to that data just by offsets. No particular order. A cluster index is the data is located next to the key. Pros for these are they're widely used and known. They're really simple and they're human readable. Some cons is they're a bit too simplistic. They don't offer solutions for every problem. A lot of ambiguity. No schemas. Okay, we'll say that one was hard. Data outlives code. Is the idea for a database, or it was the idea in the book, for a database where the code for the database could be written yesterday, but the data that was written to the database could be written 5 years ago. Encoding is taking in-memory data structures and creating binary serializations of them. Binary serialization? Serializing. No. Byte sequence. Sequence is the word I was thinking of. Byte sequence. I would say that was okay though. AKA serialization. The schemas are sick because they provide a number of benefits. Code generation. code generation, type assertions, more compact, a form of up-to-date documentation, compatibility checking before deploying changes, and we can make use of static typing and programming languages. I'll say that was hard. What are pros and cons of binary encoding? It's not human readable. So first off, pros, it can be, sizes can be reduced. It's much faster because of that. Cons, it's not human readable. And you run into forward-backward compatibility issues. Oh yeah, it's hard to agree on a structure. Reduce the size faster, and then forward-backward compatibility. So that was good. Location transparency is the idea that anything in your program thinks it's just another function in your program versus, so like when you have an API, you abstract away the fact that it's making a network call and make it just look like a function call. Yeah. All right, I need to go downstairs. I guess we'll pause here. Okay. Let's see where we at. A message broker. It's an intermediary between an application and, well, I guess between two applications. And let's see. It's probably asynchronous. The client doesn't necessarily expect a response. Oh my God. What are we talking about here? I don't know. An intermediary where messages are not sent via direct connection, but rather temporary store. Oh, I didn't know all of that. A service is what runs a server and responds to requests. No. An API that is exposed by the server. A distributed actor framework. These are all new. I haven't done these before. Distributed actor framework. Oh, so the actor framework is where everything... There's basically a bunch of actors. They all have their own state, and they can send messages to one another, but they never expect... Well... they never rely on a response. So a distributed actor framework is the same for each node can send messages to one another, but it doesn't rely on responses. Oh, thanks. Yeah, that has to be the worst card I've ever made. It literally tells me nothing. compatibility is forwards backwards compatibility. So it's basically whether the two services that are talking to each other, if they're going to be able to communicate with each other. No. Okay. The relationship between one process that encodes the data and another process that decodes it. I was like halfway there, I think. Right idea, but not quite. A server, I don't know. The one who services a client's requests. So a service exposes the API, then the server is the API servicing requests. It can act as a buffer, it can re-deliver messages to a crashed process, it can abstract the final destination. This is a message broker. Benefits of a message broker? Senders and receivers? Yeah. Okay. And now it's giving me the same thing again. A web service. Is a service that talks to web applications? Oh, it just uses HTTP. The actor model. Oh, I talked about this. Each actor is its own entity with its own state, and it doesn't rely on anything else. Model. It's a programming model for concurrency in a single process. As an alternative to dealing with threads, logic is encapsulated in the actor, and each represents one client or entity and its own state. A client is someone who connects to a server. Yeah. Horizontal scaling means getting more machines. Yeah. When each machine or virtual machine running the database software is called a node. Each with its own CPU, RAM, and disk. Coordination is done at the software level. When you get bigger and bigger machines, adding more components to a single machine. Okay. Problems with vertical scaling. Twice as much components does not equal twice the performance. On top of that, twice as many components. No, that's not it. Better components are not don't scale linearly with cost either. Replication. Replication is what am I thinking? I don't know. Keeping a copy of the same data on several different nodes, potentially at different locations. Okay. Partitioning is taking one large data set and putting different pieces in different places. shared memory architecture is where everything acts as a single machine, versus shared disk is many different machines have access to the same memory. Nice. Trade-offs between sync and async replications. Oh, synchronous replications, uh, not guarantees, but it gives durable writes, but it blocks if uh, if it gets stuck anywhere. Async provides responsiveness, but not durable writes. Yeah. Async's not here, dude. This is so annoying. Like, it's right here, and like, why can't I see it? Oh, it is there. But look, it's. Why is it doing that? Maybe if I. Oh. Cancel. I don't know. Leader-based replication is when all writes go through a designated leader. Reads can go anywhere. The leader coordinates the writes to the followers. Reads are follower only. That was, you know. Semi-synchronous is, I think it writes to one other it writes to one other follower, but not all of them. Oh, caught up. Nice. There was another one that was terrible. Let's just fix that real quick. Oh, it's probably here. There's two actually that were broken. They must be here. That's why. Alright, good enough. Replication, setting up new followers. Alright, so I think I remember most of what's going on. So from time to time, you need to set up new followers, perhaps to increase the number of replicas or to replace failed nodes. How do you ensure that the new follower has an accurate copy of the leader's data? Simply copying data files from one node to another is typically not sufficient. Clients are constantly writing to the database and the data is always in flux. So a standard file copy would see different parts of the database at different points in time. The result might not make any sense. You could make the files on disk consistent by locking the database, making it unavailable for writes, but that would go against the goal of our high availability. Fortunately, setting up a follower can usually be done without downtime. Conceptually, the process looks like this. Take a consistent snapshot of the leader's database at some point in time, if possible without taking a lock of the entire database. Most databases have this feature, as it is also required for backups. In some cases, third-party tools are needed, such as Inno BackupX. For MySQL. So you take a snapshot, copy the snapshot to the new follower node. The follower connects to the leader and requests all the data changes that have happened since the snapshot was taken. This requires that the snapshot is associated with an exact position in the leader's replication log. That position has various names. For example, Postgres calls it log sequence number, and MySQL calls it bin log coordinates. When the follower has processed the backlog of data changes since the snapshot, we can say it has caught up. We can now continue to process data changes from leader as they happen. The practical steps of setting up a follower vary significantly by database. In some systems, the process is fully automated, whereas in others, it can be a somewhat arcane multi-step workflow that needs to be manually performed by an administrator. Okay. I see. So if like a cluster was under significant read load, you might need to scale horizontally to support that during peak hours, and this would happen. Okay. Um, dude, I literally just read like 2 paragraphs and I don't know what happened. Like, I'm not thinking about it at all. Any node in the system can go down. I literally cannot. I literally cannot focus unless I read out loud. It's insane. Um, any node in the system can go down, perhaps unexpectedly due to a fault, but just, and we know what a fault is, when a component deviates from its spec. Uh, but just as likely due to planned maintenance, for example, rebooting a machine to install a kernel security patch. Being able to reboot individual nodes without downtime is a big advantage for operations and maintenance. Thus, our goal is to keep a system as a whole running despite individual node failures, and to keep the impact of a node outage as small as possible. Huh. How do you achieve high availability with leader-based replication? Alright, so on its local disk, each follower keeps a log of the data changes it has received from the leader. If a follower crashes and is restarted, or if the network between the leader and the follower is temporarily interrupted, the follower can recover quite easily from its log. It knows the last transaction that was processed before the fault occurred. Thus, the follower can connect to the leader and request all the data changes that occurred during the time when the follower is disconnected. When it has applied these changes, it is caught up to the leader and can continue receiving a stream of data changes as before. I've read the same paragraph like 3 times. It's so brutal. Okay, come on. We gotta get through this paragraph. I don't know why. Okay, on its local disk, each follower keeps a log of data of the data changes it has received from the leader. Okay? If a follower crashes and is restarted, or if the network between the leader and the follower is temporarily interrupted, the follower can recover quite easily. From its log, it knows the last transaction that was processed before the fault occurred. Thus, the follower can connect to the leader, request all the data changes that occurred during the time of the follower disconnect. When it has applied these changes, okay, so follower comes back online. It knows. Okay. All right, we got. Shoot. Okay. This is a big section. Let's try and read it, and then we'll reread it next time. Handling a failure of the leader is trickier. One of the followers needs to be promoted to be the new leader. Clients need to be reconfigured to send their rights to the new leader, and the other followers need to start consuming data changes from the new leader. This process, okay, so someone needs to become the new leader, clients need to be reconfigured, to send the rights, okay, yeah, and then other followers need to start consuming data. This is called failover. Did I read fallover? What is going on? Oh, okay. I'm not making it very far in this next one, but failover can happen manually. An administrator is notified that the leader has failed and takes the necessary steps, or automatically. An automatic failover process usually consists of the following steps: determine that the leader has failed, choose a new leader, and reconfigure the system to use the new leader. Now, determining that the leader has failed, there are many things that could potentially go wrong: crashes, power outages, network issues, and more. There's no foolproof way of detecting what has gone wrong, so most systems simply use a timeout. Nodes frequently bounce messages back and forth between each other, and if a node doesn't respond for some period of time, say 30 seconds, it is assumed to be dead. If the leader is deliberately taken down for planned maintenance, this doesn't apply. Okay. Choosing a new leader. This could be done through an election process where the leader is chosen by a majority of the remaining replicas. Or a new leader could be appointed by a previously elected controller node. The best candidate for leadership is usually the replica with the most up-to-date data changes from the old leader. To minimize any data loss, getting all the nodes to agree on a new leader is a consensus problem discussed in Chapter 9. Reconfiguring the system to use the new leader. Clients now need to send their write requests to the leader. If the old leader comes back, it might still believe that it is the leader, not realizing that the other replicas have forced it to step down. The system needs to ensure that the old leader becomes a follower and recognizes So it's fraught with things that can go wrong. The new leader, so data loss. Two nodes believe they're the leader. What's the right timeout? Wow, this is like a very hairy chapter. Dude, no way. 192. Oh, there's like 40 more pages in this chapter. Should be fun. Okay, we'll call it there. Little by little, we'll get there.